Okay. There's still a few of you left. And we can continue if you like. We are a minute early. We can continue. I'm going to have a look at actually, I wanted to make a note of the last questions that students asked, and I forgot to. Okay, so I'm going to share the textbook again, and I'll check the questions in a few minutes. Right? Okay. '53 is an interesting one. 53 is an interesting one. Question: does it converge or diverge? And I'm going to stop sharing. So 53, I'm saying, have a look at 53. Tell me whether you think that sequence converges or diverges. Let's see what people think. Does 53 converge or diverge? Okay, I'll show you the sequence again. It's 53, so there it's the one that's marked red, right? So here's what they are basically doing. The sequence starts with 0, then it's 1, then it's 2 zeros and a 1, then it's 3 zeros and a 1. So the next it's going to be 4 zeros and a 1, 5 zeros and a 1, 6 and so on, right? So the question is, does 53 converge or diverge? What do you say, NV Mokwena? CK Wu says, may we have the tutorial pages from the textbooks? Just have a screenshot including, okay. I think it's Mr. Wu. I think I did that last semester as well because you requested it. Do you not have a textbook? Okay, Ms. Opperman says it converges. MC Chirwa says it diverges. Do we use the monotonic theorem? No. Thus, you can decide whether it converges or diverges directly from the definition of converging and diverging, right? So we've had a few attempts at answering it. CK Wu, I'm still waiting for your answer about whether you've got a textbook or not. So I'm going to share again and then we'll talk. So DP Pillay says, so it diverges. Okay, let's have a look. So remember what we need to now go back to the definition of converging and diverging, right? So the definition says the larger I make the index for the sequence, the number for n, the closer the value of the function gets to one particular value. Now 53 doesn't do that. It doesn't matter how far down we go, we'll get more and more zeros, but we will eventually get another 1. So this kind of bouncing behavior between two values is one way in which a sequence can diverge. But this is a divergent sequence. On the screen at the moment, you can also see number 18, right? So 18 is 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1. There you've got 3 different values that the sequence bounces between, right? But it doesn't converge. It cannot converge because it doesn't get closer to just one particular value. And so 18 is another example of how a sequence diverges. Okay, so the answer is that one diverges. Okay, I'm going to stop and have a look at whether there are new questions. Okay, so what's important is you need to, when you do this stuff, right, when you do mathematics, you need to remember that each term we use has a very, very specific technical meaning. So when we say a sequence converges, then you need to be able to stop and remind yourself mentally what it means to say for a sequence to diverge. And you need to be able to bring these definitions back. So the way we defined these words, diverging and converging, was we first defined what we meant by the word converge, and then we said if a sequence doesn't converge, then it diverges. So in other words, to understand what it means to say a sequence diverges, you must understand what it means to say that a sequence converges. Okay? So in this way, when you're doing your tutorial problems, you are supposed to be constantly going back to the definitions to remind yourself. You know, when you're stuck on a problem, then you're supposed to be constantly going back at the theorems that we did to see which one can help you solve a particular problem. So the sequence diverges. And now let's look at BM. Mohosana says, I did not understand 47. Let's have a look at 47. Okay, so 47 is the sequence 1 plus an is 1 plus 2 divided by n raised to the power n, right? So 47, let's remind ourselves what the instruction is for 47, right? It says determine whether the sequence converges or diverges. If it converges, find the limit. So 47. So 47 is the an is 1 plus 2 divided by n raised to the power n. So I'm scribbling here to see if I can change this a little bit. So I rewrite this as an is 1 plus 2 over n raised to the power n. Inside the bracket, I'm going to make it n plus 2 divided by n raised to the power n. Okay, so I'm going to stop sharing. Everyone's had a look at the sequence, the general term, 1 plus 2 over n raised to the power n. Remember now, as n gets bigger, I'm multiplying more and more of these factors together, right? So when n is 1, So A1 is the term 1 plus 2 divided by 1 raised to the 1, which is 3. A2 will be 1 plus 2 divided by 2 raised to the 2, which is, it's going to be 2 squared, which is 4. A3 is going to be 1 plus 2 divided by 3 cubed, right? Which is 1 2/3 raised to the power 3. A4, what do you think? Let's see what people in the TUT says. Okay, so DPPLA, when will you be releasing the video on example 14? As soon as I get my software to work properly. And DPPLA says it converges as n approaches infinity, the limit approaches 1. Okay. As n approaches infinity, the limit approaches 1. That is 47. Was it 47? Mr. Naika, for the moment, yes, that's what we know. At this stage, we are working on the assumption that everything is online. 47. Okay. So I think to come back to 47, I'll make some last comments. I think here I would use, because I've got an exponent, because I've got n in the exponent as well, I would try and use again the ln function, because if I use ln, I can get the exponent as I can get rid of the exponent, right? And then I can take the limit and see if I can use something like L'Hopital's rule. Okay. Okay. So I do think it converges, but I'm not sure if it will converge to 1. Okay, let's try 82. Let's have a look at question 82. Question 82. Question 82. What was that one? Okay, so show that the sequence defined by A1 equals 2 and an plus 1 equals 1 over 3 minus an satisfies the condition that it's bounded by 0 and 2 and is decreasing. Deduce that the sequence is convergent and find its limit. Okay. So an plus 1 is 1 divided by 3 minus. So first we want to show that the sequence, we want to show that an is always greater than 0. Right? How easy is that to see? Well, we start with a1. We start with a1 equal to 2. So maybe the second inequality is easier to show, that an is less than or equal to 2. So A1 is 2. A2 is going to be 1 divided by 3 minus 2. So that's 1 over 1, it's 1. A3 is going to be 1 over 3 minus 1, which is 2. Right? So it's 1 over 2, it's a half. Okay, so now you've seen what it does for the first few terms. I wonder if it would make sense to try and use mathematical induction. I wonder if it would make sense to use mathematical induction. Yeah, so make a statement. Let the statement be something like an plus 1 is greater than 0 and less than an, or less than or equal to an, which is less than or equal to 2. Then we know that P1 is true, because P1 is the case where n is equal to 1, and so an plus 1 we've seen is less than 2. Then assume that Pn is true, which means we know that an plus 1 must be less than an. Okay, so I would tackle it using mathematical induction. Okay, let's see. I'm going to stop sharing. I wish I could see what students are writing without. Can we know that the sequence is converging because of the monotonic sequence theorem? Yes, it would. If you can show that the conditions of the monotonic sequence theorem are satisfied, then you would be able to conclude that it's converging because of that theorem. That is correct. Okay. Let's have Mohosane asks about 47, but we've looked at that one already. Any other questions you want to look at? We still have a little bit more time. So clearly, it's not possible for me to, in this setup, write things out. But we can talk about them and I can give you pointers. It's better that I don't solve it for you in any case, in any way, in any case. Does an greater than 0, less than 2 mean the sequence is bounded? Still for 82? Yes. So when you say, Ms. Opperman, when you say does, so I'll type it here. So your question is, does 0 less than or equal to, remember, less than or equal to, or I think in this case it's less than a of n, less than or equal to 2. Now here's the important thing, for all n in the set of natural numbers mean that the sequence is bounded. So that's the important thing. You must say that those conditions hold for all n in the set of natural numbers, then that means the sequence is bounded above and bounded below. Bounded above by 2, bounded below by 0. Okay. Mr. Naika, tutorials, solutions a little bit later today, tomorrow at the latest. And then going forward from this week, you'll get them a week after after the questions were posted. Okay. Okay, cool. More questions? Mr. Wu, I'm still waiting to find out if you don't have a textbook. Is that why you want me to post the questions? Or Miss Wu, I'm not sure if you are Mr. or Miss Wu. Okay, yes, but now it's fine. I don't understand what that means. Okay, so what I'm going to do then is I'm going to make a photocopy of the pages that have the questions on. Oh, you've sorted it out. Okay, cool. So then I won't make that effort. Okay, any more questions? Okay, cool. So there are still people who are using 7th edition, so that's fine. So I'll make photocopies of the questions with of the pages with the questions, and then I'll post them. Yes, you are correct. The questions are not the same for the 2 editions. Okay, no questions coming up. Let's open the questions again and just randomly have a look at some of them. Okay, let's see if we can pick up some interesting ones. So 83 is definitely an interesting one, the one that Ms. Opperman started us off on. So let's have a look at the ones that you can see there, the 72 to 78, right? Determine whether the sequence is increasing, decreasing, or not monotonic. Is the sequence bounded? How about 75? Let's look at 75. Is it increasing? Is it decreasing? Or is it not monotonic? And then finally, is the sequence bounded? So 75, A1 will be -1. A2 will be 2. A3 will be -3. A4 will be 4. Can you see the pattern now? So now the question is, so now I'm going to check what you guys are saying in the chat window. Is it increasing, decreasing, not monotonic, and is it bounded? 75. Okay. Okay. Not monotonic. Pillay says not monotonic. Flongwane, not monotonic, not monotonic. 75 is increasing, not monotonic. Okay, so not monotonic is correct. It jumps up and down, right? So it'll become, it's +3, -4, that kind of thing. Actually, -3, +4, -5, +6, and so on, all right? Is it bounded? No, it's not bounded. It can't be bounded. It can't be bounded above, and it can't be bounded below. At some point, you will hit a value for n. So how do we know whether a sequence is bounded? If it's bounded above, there must be some number with a property that the sequence never reaches a value bigger than that. But clearly for the sequence, it's not the case. If you pick the number 1,000,000, it's a big positive number, all you have to do is to let n go to 1,000,001. Because it's an odd number, right? The power in the exponent there will be odd, and so you'll get, actually no, sorry, 1,000,002. It's a positive number, it's an even number, and so the power there will be even, and so it'll be bigger than 1,000,000. Okay, and you can do a similar explanation for any large negative number. It's not increasing, it's not decreasing, right? It's not increasing, it's not decreasing, it's not bounded. Okay. Ms. Opperman says, can a sequence have a lower bound but not an upper bound? Yes, that is correct. The sequence an equals n has a lower bound but not an upper bound. The lower bound for the sequence an equals n is 1 or 0, right? Why is this one not bounded below? It's not bounded below because if you take any number that you think is a lower bound, you'll always be able to generate an element of the sequence which has a value smaller than that lower bound. Could -2 not be a lower bound? No, -2 could not be a lower bound because I can easily generate -15 from that sequence, which is less than -2. Ms. Opperman, does that answer your question? Okay, so I mean, this stuff requires thinking. You know, you need to constantly double check whether your understanding of things is correct. And this is normal, by the way. dp per A, because there is a value that will be less than -2 if you carry on generating 100% correct. That's exactly what it is, dp per A, right? Okay. I'm happy with this session. I'm happy that we've had a chance to talk about this stuff. The material is challenging. It's more challenging than first year mathematics, so please do a little bit every day. Read it, ponder the definitions, try out the examples. With the examples, what I like to do is I sometimes cover them and see if I can complete them on my own. Okay? So this is how you do mathematics. You must do it. You can't learn how to ride a bike by watching someone else ride a bike, right? You've got to get in there, get on the bike, you know, fall, scruff your knee, get up, get back on it. Okay. Okay, cool. Let's have a look at another one. There aren't any new questions coming in. So that was 75, the last one we looked at. What about, let's pick something different. Okay, it occurs to me there's something I should explain about how we will approach the module. So you remember that this is outside of, well, it does touch on tutorial problems. So maybe I'll pick an example and show you. Okay, so look at the questions 19 to 22. Now you'll remember in 1A and 1B, we said to you that calculators are not allowed, right? And this is in general the case for all maths modules. And so I haven't said so explicitly yet, but I'm starting to sing that song now, because I don't want you to spend too much time calculating answers like in 19 to 22. It says calculate to 4 decimal places the first 10 terms of the sequence, okay? I'm not going to ask you to do things like that. I'm not going to ask you to calculate to so many decimal places. In fact, I don't think you will ever need to use a calculator in this module. And I would guess for most of the other maths modules that you're doing as well. So our focus will always be on trying to do what you can using pen and paper. Okay? So going forward, I'll update the study guide to say that you'll never need to use a calculator and that you should never use a calculator. It's quite important. Okay? I'm going to stop sharing and have a look at whatever comments have come in. Could we write down other questions outside the tutorial? Yes, of course, Mr. Wu. Yes, any problems? Anything? Well, hopefully you'll stick to this textbook. But yes, anything relating to sequences and series. Can you please explain example 8 on series? Okay, we've got about 10 minutes left. Let's switch over to example 8. Okay, so we haven't done example 8 on series yet. So Ramarumo, we stopped yesterday's lecture. We stopped at example 6, but we can. Okay, so let's do example 5 then, because 5 we did cover in the lecture. We'll look at 5 from this week's. So Ramarumo, you said series, so I'm thinking that's 11.2. So let me get 11.2, and let's start with example 5. Okay, so now I'm going to share my screen. We'll look at example 5 and example 8 from series. Okay. And so there's example 5. Okay, so example 5 was quite lengthy one, which was sort of a practical kind of one. So a drug is administered to a patient at the same time every day. Suppose the concentration measured in milligrams per milliliters is Cn after the injection on day N. Before the injection the next day, only 30% of the drug remains in the bloodstream, and the daily dose increases the concentration by 0.2 milligrams per milliliter. Find the concentration of the drug after the injection on the third day. Question B says, what is the concentration after the nth dose? And number C says, what is the limiting concentration? Okay. So let's do this one again. Here we go. Now, given that setup, the first one says find the concentration of the drug after the injection on the third day, right? So now, just before the daily dose of medication is administered, the concentration drops to 30% of the previous day's concentration. In other words, whatever the concentration was on day N, just before the injection on day N plus 1, 30% is left from day N, right? The concentration. And then we add the new injection, right? So we're going to set up a relationship between the concentration on day N plus 1 and the concentration on day N, right? And that's what it looks like. Because remember, whatever the concentration was on day N at the point of injection, the model tells us, the story tells us that 30% of that is left at the point where we inject again. And when we do inject, we add 0.2 milligrams per milliliter to the blood, right? And so our equation, it's also called a recurrence relation, right? It gives the concentration, it gives the value of the variable at this point in terms of values of the variable in previous points. And so Cn plus 1 must be 0.2 plus 0.3 Cn, right? And now we can, knowing this, we can plug in values for N. We start by saying, and now for some reason I can't see that properly. I'm not sure if you can. So I'm going to no. We can start with C equal to 0 and start, see if I can make this a bit smaller. No. So this is because I'm trying to make these things fit into the application. So let me stop quickly. I'm going to recompile the file and then I'll start sharing again. Right? Let me stop sharing for a minute because it's the work that I've been doing in trying to get the recordings to work, which is causing this to show up in an incorrect way. Okay, you give me 10 seconds, then we can start moving again. Okay, let's try this again. Okay, that's going to work better. Okay, so I'm going to share my screen again. Okay, and now you should be able to see it. So now we can start with C0 equal to 0 and putting N equal to 0, 1, and 2, plug it into the above equation, we get C1 is 0.2 plus 0.3 C0. Now C0 is 0, right? On day 0, there's nothing in the blood and we don't do anything, right? So C1, immediately after the injection, there's only the amount of drug in the person's blood that we injected. And that makes sense, right? It's 0.2. What about the second day? Well, the second day, we get the 0.2, which we've just introduced, plus 30% of what was left from before. And our equation allows us to just plug these values in now, right? So C2 is 0.2 plus 0.3 C1, and C1 was 0.2. Plug it in, we get 0.26. C3, same idea. C3 is 0.2 plus 0.3 C2. And if you calculate that, you get 0.278. Okay, what is the concentration after the nth dose? After the nth dose, our expression needs to look like this. Cn is 0.2 plus 0.2 times 0.3 plus 0.2 times 0.3 squared, and so on, all the way to 0.2 times 0.3 to the n minus 1. And this we recognize as a convergent geometric series. It's convergent because the common ratio r is less than 1, right? Its absolute value is less than 1. And so we can plug it into an equation, and for C3, we can plug it into an equation to get, let's do that one, to get an expression for the nth dose, or the concentration after the nth dose. That's 2 divided by 7 times 1 minus 0.3 to the n. Right? What is the limiting concentration? When we say limiting concentration, we mean, suppose we do this every day. So n represents the number of the days. So here we've got a patient who has to get this injection. Maybe it's someone suffering from some chronic disease. He must get this injection once a day, every day for the rest of his life, right? So what is that? What is the limiting concentration? At what point will the concentration become stable? What's that point? And so the limiting concentration can be calculated by taking the Cn and calculating the limit as n goes to infinity for that expression. And when we do that, the limit as n goes to infinity of 0.3 to the n is 0, right? And so we get 2 divided by 7. Okay, I'm going to stop. I'm going to stop sharing and have a look at questions. And I think that's it for today. So we'll do Ramarungo. We'll continue with example 8 as part of tomorrow's lecture. And then hopefully by next week, the software will work and I will be able to post recordings of the lectures. Also, it's quite possible that next week, one or more of the tutors will be taking this tutorial session. Okay, so see you tomorrow evening. Thanks for coming. Cheers.